So one has to be very careful while just looking at epsilon much less than 1 and then considering, okay, this is a small term, let's drop it out to find the leading order solution, and you go ahead and solve this, then you cannot solve both the boundary conditions. So let us first evaluate its full solution. So this is a second order ODE, you can solve it very easily. Okay, you can solve it very easily. So first integration will give you something like this, okay, where this C1 is some arbitrary constant, and then I can multiply. So I can divide this equation by epsilon, and then I can multiply with e to the power y by epsilon. This is the integration factor, and then C1 1 by epsilon C1 minus y square by 2 e to the power y by epsilon. Okay, you can multiply the integration factor, complete the derivative here and get this form, and then we can integrate this equation further, and I can write this is, so 1 by epsilon. So C1 times e to the power y by epsilon integration, what would it be? So this would be e to the power y by epsilon divided by 1 by epsilon, so epsilon minus an integration y square e to the power y by epsilon dy. Okay, and then since we are doing indefinite integrals, plus some C2, and these C1 and C2 we will find when we use the two boundary conditions. Okay, so u e to the power y by epsilon equals, so this basically becomes simple, and what is this? What is y square e to the power y by epsilon? Hmm? What is y square e to the power y by epsilon? So we can calculate it using by parts. So we will have y square e to the power y by epsilon times an epsilon minus 2 times y e to the power y by epsilon dy plus C2, which is here again we can apply by parts. Right. So you will get one epsilon after one integration and then another epsilon and then a plus C2. Okay. So we can take this, we can divide this equation with y e to the power y by epsilon, and we will get E is, we can also cancel one epsilon from every term. Okay. And then we'll get U is equal to C1 plus C2 e to the power minus y by epsilon, and then a minus y square by 2 from here, and then from here plus epsilon y, and then from here we will get minus epsilon square. There should have been a minus sign here. Okay, so this is your full solution. We can find C1 and C2. So you substitute this and you substitute this, and your eventual solution will be 3 by 2 minus epsilon e to the power minus y by epsilon minus 1 e to the power minus 1 by epsilon minus 1 plus this. Now this seems to be an exercise in just ODE solving, linear ODE solving, okay, but there is a lot of meaning here when we go ahead and apply this to fluid mechanics. Okay. So, before we translate our understanding of from this equation to fluid mechanics, let us now do what I was saying we should not do and see what we get. Okay. Let us just drop this epsilon term and let us just see what we get. Okay. So, when we drop epsilon term, so let us say we are saying that epsilon is much less than 1, and as a result of this we are saying that epsilon d2u over dy square is much less than 1. The order of magnitude of this term is much less than 1. So, in a way we are claiming that the d2u by dy square term is of order 1. We are claiming that d2u by dy square is not going to be very large. Okay, we are claiming that, we are assuming that, and we are proceeding with this claim, and we are seeing what we will get. So, let us do this and see what we get. So, we get du by dy plus y equals 0, which means u is equal to some constant minus y square by 2. Okay. This simply means that u is some constant minus y square by 2. Okay. And now we have an ambiguity here in a way, that which boundary condition can we satisfy for this one, which boundary condition can we satisfy for this solution. We have dropped epsilon much less than, due to epsilon much less than 1, we have dropped this term epsilon d2u by dy square, we have dropped that term. So, which boundary condition can we apply? Do we apply u of 0 is 0, or do we apply u of 1 is 1? And if we choose 1, how do we logically reason it out that there is a reason why we choose one boundary condition? Hmm? So, one way in which you can reason it out is, in this particular problem, since you know the full analytical solution, okay, in this particular problem you know the full analytical solution. So, what you can do is you can evaluate the limits of this function close to y tends to 0 and close to y tends to 1. Okay, not limit in the sense the value of the u, because the limits will give you the values which are the boundary conditions, but you want to evaluate, let us say this is u and this is y and this is y equals 1, and let us say this comes out to be something like this. Okay, so you don't want to evaluate the values here, but you want to know what is the functional form close to these limits. Okay, so you're not supposed to just evaluate the limit as a number, as a value, but you want to understand what is the asymptotic form. Let's call it the asymptotic form as y tends to 0 or y tends to 1. So, how will we reason it out? For y tends to 0, for y tends to 0, how will we reason out that what is the asymptote of this function? How will we find it? The asymptote of the function for y tends to 0 or y tends to 1, either one. Hmm? So, I will leave this as an exercise to you, and I will give you a different reasoning. So, find asymptotes. I do not know if you guys are. So, find asymptotes of u for this and for this. Okay. And whichever asymptote can match this functional form, we will know that, okay, that is the boundary condition that can be satisfied by this boundary by this function c minus u y square, c minus y square by 2. I am going to give a reasoning which is very similar to the fluid mechanical reasoning, and the reasoning goes something like this. We said that d2u by dy square, from this we are saying that order of d2u by dy square is 1. Okay, order of magnitude of this term is order 1. If you look at the variation of u is 0 here and u is 1 here. So, this is 1, okay, this is 1, this is 0. What I am saying is that the variation, the second order derivative, or it is in a loose sense you can call it variation. What I am saying is that the variation of u with respect to y is not very large. Okay, the variation of u with respect to y, if it was very large, then this term wouldn't have been wouldn't have been much less than 1. So, what I am going to say is that variation of u with respect to y is not very large. So, it cannot be somewhere close to y tends to 0 boundary. It cannot be somewhere close to y tends to 0 boundary, because at y tends to 0 the boundary condition is that u of 0 is 0, and it has to reach all the way to u of 1 to be 1. Now, some of you may say, oh, why couldn't the solution, if this is how the solution looked like, then close to y equal to 1 the variation is large, not close to y equal to 0, and you would be right. Okay. So, for all of these reasonings we need to know how the analytical solution actually looks like. Fortunately, when we go to fluid mechanics, we do not need to know the analytical solution, we have a very physical type of a reasoning why one particular boundary condition will be satisfied here. So, from the analytical solution, using both the reasonings, either you find asymptotes or you say you plot the function and see where the variation of u is large. We conclude that we will conclude, I mean you will have to plot it and conclude that for y equal to 1 this u is going to satisfy this boundary condition, and we will get, so C will be 3 by 2. So, this implies u of y will be 3 by 2 minus y square by 2. I am going to label this solution as, instead of u, I am going to label it as u o. Okay. And now let us try to find the other side of the story. Clearly, this guy does not satisfy u of 0 equals 0. It cannot. Okay. This solution cannot satisfy u of 0 equals 0. Okay. So, at best this function, this 3 by 2 minus y square by 2, this is some kind of an asymptote of this actual solution, and the asymptote, this asymptote is matching with the exact solution close to y equal to 1. Okay. So, it is going to follow a curve, and that curve is going to match your analytical solution close to y equals 1. But for y equals 0, this guy has a value of 3 by 2. I mean technically this will be even not like this, but this will be like this. Okay. At actually it has maxima at y equal to 0, no? So, it will be like this. So, this solution, this is u o, this is your u of y. So, in a way what you have ended up calculating is the solution for far away from the y equal to 0 boundary. Far away from y equal to 0 boundary, the solution asymptotically matches the analytical solution. What can we do close to this y equal to 0 boundary? What can be done close to y equal to 0 boundary? And the reasoning goes something like this. Instead of taking y as our independent variable, I will say y equals some epsilon times c. And by writing it like this and claiming that c is less than infinity greater than 0, I am claiming that y is a coordinate which is varying from 0 to some small value, but c is a coordinate which is stretching it. So, if you have y varying as, let us say 0, 0 0.01, 0 0.02 and so on, and let us say your epsilon is 0 0.01, then your c is varying as 0, 1, 2 so on. So, in a way what you have done is, you have taken, let us say this is your y equal to 0 boundary, what you have done is you have stretched your coordinates here, okay, and now you have defined a new independent variable c which scales with this epsilon to give you y. And the power of this rescaled coordinate, so this is a rescaled coordinate, this c we will call as a rescaled coordinate. The power of this is that du by dy now becomes 1 by epsilon du by dc, okay, and d2u by dy square becomes 1 by epsilon square d2u by dc square. And now when you substitute that, in this equation, you will get 1 by epsilon d2u by dxc square plus du by dxc plus an epsilon xc equals 0. This is your rescaled equation. This is your rescaled equation. Just try to follow this as a maths class for 5 to 10 more minutes, and then we'll pour fluid mechanics inside it. You will by looking at the analytical solution. In your notes, you can just go ahead and write by looking at the analytical solution. You have to know what is the analytical solution. It is varying as this parabola, and I am saying that only for y. So, you can calculate its asymptote for y tends to 1, and you will get that this is a parabola. Just look at it, you will see this is e to the power minus 1 by epsilon, e to the power minus 1 by epsilon, this becomes 1, and this becomes some epsilon y minus y square by 2. So, this whole function behaves like a quadratic near y tends to 1. So, it is a parabola near y tends to 1, and from there I concluded that okay, if I am getting a parabolic form, then it has to be close to y equal to 1 rather than close to y equal to 0, because close to y equal to 0, if you apply the y equal to 0 limit, you will get an exponential also remaining. Just evaluate that limit. These guys won't cancel out. So, this is your rescaled equation, and now what we will do is we will solve this equation. We will solve this equation at the leading order. So, at leading order, we will get at leading order we have d2u by dxc square plus du by dxc equals 0. Okay, this is separate discussion. I am continuing here. So, at leading order we have d2u by dxc square plus du by dxc equals 0, which means du by dxc plus u equals some constant c1, and then what is the solution of this? We have d by dxc, du by dxc as c1 minus u. So, we get log of minus log of c1 minus u equals c minus some log of constant a, and so is if I call this as some constant c2, let us write. So, this gives me c1 minus u is c2 times e to the power minus c. So, u is simply c1 minus c2 e to the power minus c. And now, since I am evaluating for small y, so in the limit in limit y tends to 0, we have c also tends to 0. So, limit y tends to 0, value of c is also 0. Okay. So, this is not something very straightforward, but I am going to skip the mathematical details here, and I am just going to write this is the condition that we have. So, u of c equals 0 is equal to 0, which means c1 minus c2 equals 1. Oh, c1 minus c2 equals 0. So, that means your u of c is some c1 into 1 minus e to the power minus c. And replacing this c with y by epsilon, I am going to denote this with a ui as a function of y. So I'm going to write it as 1 minus e to the power minus y by epsilon. And now the question is, when we did this rescaling of coordinate and we got the rescaled equation, we needed two boundary conditions because we did not get a first order equation now. We retained the order of the equation. So what is the second boundary condition? Where do we get the second boundary condition? And that is actually the title of today's lecture, which was matched asymptotics or asymptotic matching. And what we say is that for limit y tends to 0, u of oy should be equal to limit c tends to infinity u of I of c. Either you want to write it as c or y, it does not matter. And what we are saying is that in these rescaled coordinates, so let us say you have some rescaled coordinates here, okay, you have some rescaled coordinates here, meaning for some up to some values of y you have stretched in a way that this finite value of y you have sent it to infinity. And what we are saying is that the limit of this stretched coordinate tending to infinity, the value of this function at that limit should actually match with this value that the outer solution, the UO solution was giving you. Okay. And this basically gives you, so what is y tends to 0 limit here? It is 3 by 2. What is limit c tends to infinity for ui? That is c1. So that means u of I of y completes as 3 by 2 into 1 minus. So that means if you were to evaluate this function, if you were to plot this function, so for y tends to infinity, what is the asymptote of this function? What is the asymptote of this function for y tends to infinity? 3 by 2. So this function will actually look something like this if you were to plot it. And in a way what we have done is, although in this problem calculating that analytical solution was straightforward, what we have found are two caps of the analytical solution at both the boundaries. Okay, you can plot them and make sure that this is how they look. Okay, terminology wise, this is called an outer solution and this is called an inner solution. And now where does fluid mechanics comes into here? Where does fluid mechanics play a role in all of this discussion? And what I want you to look at is, instead of this equation, recall our dimensionless Navier-Stokes equation. So I'm going to drop all the stars just for my convenience. This is the dimensionless Navier-Stokes equation. And look at it in the limit of large Reynolds number. So let us say when Reynolds number is large, this 1 by Re is some epsilon which is much less than 1. Okay. So I'm going to replace this 1 by Re with epsilon. And instead of in one dimension, in 3 dimensions, we have a similar situation as here. We have an epsilon multiplying the highest degree term or highest order term. If you simply drop epsilon naively, which is what we did when we found the outer solution, what will you end up with? If you drop epsilon naively, what will you end up with? The equation at leading order will be this guy. Okay, I am assuming that del dot u is always there in the background. So that is not something that I need to specify. So if you just drop this epsilon term naively, you end up with this equation. What is this equation? This is equation for which kind of a flow? This is an equation for which kind of a flow? This was not done in your, I mean, inviscid flows and ideal flows you should have covered in your introductory fluid mechanics course, no? So this is inviscid flow equation. Technically inviscid incompressible flow. And the idea is that inviscid flows technically are not flows of fluids which have zero viscosity, except for fluids which display quantum behavior such as supercooled superfluid helium. There is no fluid of practical interest which has zero viscosity. Okay. And just because you have small viscosity doesn't mean you can approximate any flow to be inviscid. Remember, the dimensionless equations don't care about viscosity, they care about the Reynolds number. You could have small viscosity, but you could also have very small length scales to make the Reynolds number not so small or not so large. Okay. The idea is that your Reynolds number, in the limit of large Reynolds number, only the outer solution follows the inviscid flow equations. What does this outer solution mean? So if you again remember this picture and now imagine flow past some surface. Okay, imagine flow past some surface. When we derived these equations, we took the same length scale in both x and y and z coordinates. We took the same characteristic length scale in x, y, z and z coordinates. So if you are, let us say, somewhere far away from the boundary where you are you can take the same length scale in x, y, z coordinates, then out far away from this boundary you can say that your outer solution will be valid. What that means is that far away from the boundary you can assume your flows to be inviscid in nature, provided that your Reynolds number is large. Provided that your Reynolds number is large. For example, in this kind of a surface, let us say if we take the radius of curvature of this surface as the length scale, then any Reynolds number that is defined using that radius of curvature, if that turns out to be large, then sufficiently far away from the surface, sufficiently far away means the distance from the surface should be of order of that radius of curvature, should not be very small compared to that order radius of curvature. Sufficiently far away from that surface, your flow obeys inviscid flow equations. And now instead of, so we don't know the analytical solution of this equation just like we did in this case, but we have some physical boundary conditions and physical reasoning which can help us out in determining which boundary conditions will take a hit when we specify inviscid flow, which boundary conditions will take a hit. Some boundary conditions have to take a hit because we don't have second order equations anymore, we have first order equations. Which boundary conditions will take a hit? Which boundary conditions will not be applicable anymore? No slip. So inviscid flows cannot obey no slip boundary conditions, and you will actually solve the flow without any no slip boundary condition. If you have a surface, you can, all you can say is that u dot n is 0, that on a surface the boundary condition that you can implement, assuming it a hard wall of course, if it was porous wall or something else then you will take that boundary condition, but the idea is you cannot impose a tangential boundary condition on inviscid flows, because the virtue of no slip boundary condition was viscosity and you have dropped the viscous terms, you have completely dropped the viscous terms. You cannot impose boundary conditions due to a physical phenomena which you don't have in your governing equation. Okay. So no slip boundary condition will not be applicable anymore. So we have one set of boundary conditions which we have removed. Now we have a closed system, first order equations, single set of boundary condition in each direction. And now what about this other side of the story, the rescaled coordinate one? And the idea there is that, let me draw a picture here, that when you have a flow, when you have a flow past a body, and let us say you are very close to the surface, let's say this is a tangential coordinate, this is a normal coordinate. When you are very close to the surface, let's say the flow is coming at a speed u infinity and very close to the surface, technically in reality we will apply no slip boundary condition. So, the tangential velocity here has to go to 0, okay, but our outer solution cannot give us that. The inviscid flow solution cannot give us that the tangential boundary condition be 0 because it cannot support those boundary conditions. So, technically whatever flow velocity you have in the inviscid region or in the outer flow region, it has to drop to 0 in a very thin region next to the surface. And in that thin region, what you will have to do is you will have to rescale your coordinate. Once you rescale your coordinate, what you will see is that all the terms of epsilon del square u do not drop out. And that is the whole discussion of boundary layer theory. What is boundary layer? Boundary layer is this small region next to the surface where you cannot ignore the viscous effects. Once you rescale the coordinates, your epsilon del square u will have some order 1 terms. Not all terms will be small. And at leading order, you will be forced to have a second order derivative here. And then the question is, okay, how do we find the full solution? The way we find the full solution is by doing asymptotic matching. We will find an, just a second, we will find an inviscid solution, we will find the boundary layer solution, and then we will asymptotically match them. Okay, this asymptotic matching is something that you should understand very thoroughly, because when we go to boundary layers this will be used. If you focus on this discussion, then you see that for outer solution we didn't really need asymptotic matching. Outer solution was just a naive evaluation. Okay, if I give you this equation, you will say, oh, epsilon is much less than 1, let me just get rid of this term and evaluate at leading order what is the solution. Yeah.
While evaluating u at y is equals to 1, we will be using outer solution, while at y is equals to 0, we will be using the inner solution.
So at y equals to 0 and y equal to 1, we don't need to evaluate through our solution, that is just
Near
from the boundary. Yeah, near y equal to 1 and near y equal to 0, we will have to account for two different solutions. And as you can see, I have obviously drawn this as an exaggerated picture. If you look at this, if you go ahead and plot them in MATLAB or Python, you will see that this is your analytical solution, this is how this looks, and this is how this looks.
middle, we can't evaluate.
So in the middle, the answer is that in the middle you are approximating the solution with some error. If you recall, then whenever I am dropping these terms, I am always writing that this is the leading order solution. There are further corrections. There are further corrections that are to be evaluated. We don't care about them. Okay, as far as this course is concerned, we are always going to be bothered with leading order solutions. Okay, what are the leading order solutions? So once we do this asymptotic matching, okay, there is a way in which you can actually calculate the composite solution, which is called composite solution. In the textbook you can see it. So this is called composite solution, and the idea of composite solution is that it is u inner plus u outer minus the common part. And just to remind ourselves that this is not equal to the analytical solution, this is an approximation of the analytical solution, we have to notice that there will be order epsilon corrections in this solution. So the common part here will be 3 by 2. The common part is that asymptotic matching limit, which will be 3 by 2. So what you will do is you will add these two minus a 3 by 2, and that is your approximation to the solution at leading order. That is not the full solution. So if you look at notes, I have given a example of how to use this asymptotic matching method in a simple fluid mechanical scenario also, where you don't need to go over this inviscid flow and viscous flow kind of discussion. Okay, and that example is taken from a textbook only. So I'm not covering something very advanced or extra. It is from the textbook. Okay, Panton's textbook you can look at, and there are further examples which we can discuss where asymptotic matching is used. But what I want you to know is understand the motivation of looking at inviscid flows and boundary layer theory as two separate parts whenever we are looking at high Reynolds number flows. Okay, going back to our previous lectures, we were looking at high Reynolds number flows now. Okay, we have finished our discussion for low Reynolds number flows. Moderate Reynolds numbers are not very interesting to us because eventually we'll end up with the full governing equations that we have to solve. We want to know what are the approximations that we can make. So we turn to the other extreme of high Reynolds number flows. Questions? Yeah. Huh? I don't know what that word means, most prominent for high Reynolds number flows. Boundary layers are always there. We tend to make an analysis by distinguishing a boundary layer and an inviscid flow regime when we are dealing with high Reynolds number flows. We will always have some kind of boundary layer. If it's thick of the order of domain size, that's also a boundary layer, right? So that's a very wrong line of reasoning, because boundary layer, the distinction between boundary layer and an inviscid flow appears due to high Reynolds number flow regime. Okay, in the low Reynolds number flow, there is no requirement of making this distinction boundary layer. You shouldn't say we did not account for a boundary layer. The reason why we need a boundary layer in high Reynolds number flows is because outer solution is not able to satisfy the no slip boundary condition. In low Reynolds number flows, we did not have this problem where outer solution and inner solution were different. Forget about flow past Stokes flow past a sphere or something where we talked about outer field and inner field, but we just solved for the full flows over the whole domain. Okay, because the governing equations that turned out were linear for the flow everywhere. So we just ended up solving those equations. We need that boundary layer concept in high Reynolds number flows to be able to match this no slip boundary condition, because the outer limit cannot match no slip boundary condition. So it is not right to say that we did not account for boundary layer in the low Reynolds number flow regime. There's no concept of boundary layer there. There's no distinction between a boundary layer and a non-boundary layer flow there, because these asymptotics don't apply. They are actually reversed. You have 1 by Re, which is very large instead of being very small. Okay, so in a way, the non-dimensional equation is showing you that the most dominant effects are actually viscous effects. Does that clarify? But yeah, it's a very natural doubt to occur, uh, that why are we doing this distinction between boundary layer and inviscid flows now, and The only reason is then in low Reynolds number flows we had 1 by Re which was much less than 1. So instead of thinking of this equation like this, it was actually something like 1 by epsilon. Okay, so the whole situation was reversed. So for a couple of lectures now we are going to look at inviscid flows in detail. Okay, and when I say inviscid flow, I do not necessarily always mean an ideal flow. All inviscid flows are not ideal flows. There is a specific class of inviscid flows which are called ideal flows or irrotational flows, and we'll get to them in a minute. The governing equation, again we are looking at incompressible inviscid flows. The governing equations are these. So in the dimensionless form they are this, and in the dimensional form there will be a row appearing here, that's it, and then you have a del dot u equals 0 as well. So these are the dimensional governing equations of inviscid flows. Okay. For steady inviscid flows, if you look at steady inviscid flows, you have u dot grad u plus grad p by rho equals 0. Again incompressible all the way. So rho, just imagine this rho to be a constant. Okay. Now if you go back to your index notation exercises, we have shown that this u dot grad u is actually equal to, so this guy is equal to what? Grad of mod u square by 2 minus u cross omega. Okay. So I'm going to substitute that here, and what I will get is that grad of p by rho, again grad of p by rho is simply grad p by rho because rho is constant. So I can take this rho inside. Okay, and this is a very important concept because this thing will not be applicable whatever we are doing. You have to write a separate type of equation when you look at compressible flows or flows with changing density. Equals u cross omega. Okay. Now if I define a function b which is p by rho plus mod u square by 2, then I note that grad of b is u cross omega. डिस्को लाइट बंद करो यार. Thanks. So grad b is u cross omega. What does this mean? So if I say that b equals constant, if I look at the surface of b equals constant wherever in 3D space this b is constant, then grad b we know is going to be pointing towards the normal of this surface. Okay, if I have b equals constant, then grad b is parallel to the normal of the surface. Okay, grad b is parallel to the normal of the surface. Now u cross omega is a vector which is going to be perpendicular to both u and omega, right? U cross omega is going to be a vector which is going to be perpendicular to both u and omega. So if grad b is perpendicular to both u and omega, that means locally at this point, if grad b is perpendicular to u and omega, then at this point u and omega, they may not be perpendicular to each other, but they lie, or the lines which define this u and omega, they will be inside this b equal to constant plane. Okay, the lines of u and omega will be forming the b equal to constant plane. Okay, and that tells us, so let us say these are the lines of u and omega. What do we call those lines which are always parallel to u? Huh? Streamlines. And these we call as vertex lines. So on the surface formed by vertex lines and streamlines, we have b equals constant, or p by rho plus mod u square by 2 equals constant, which is the Bernoulli's equation. Okay, so your Bernoulli's equation, which we tend to apply everywhere, is applicable only for steady incompressible, which is between the lines always in this course, steady incompressible inviscid flows. That is when you can apply Bernoulli's equation, not between any 2 points, only along streamlines or vertex lines, or on the surface defined by streamlines and vertex lines, which is a very contorted way of thinking about these things in actual fluid flows, because in actual fluid flows it will be just easier to visualize streamlines and apply this across 2 points of streamline. Okay. So this p by rho plus mod u square by 2 equals constant only when you are looking at steady incompressible inviscid flows, and we are, remember, where does incompressible assumption come into picture? When we derive this, we have a del dot u that appears, which we substituted to be 0. Okay, so this substitution is possible only when del dot u is 0. Okay, so your Bernoulli's equation is valid only in the surface where, or surface which is formed by streamlines and vertex lines. Now, before we discuss another class of inviscid flows, which are the ideal or irrotational flows, so what about unsteady inviscid flows? So in unsteady inviscid flows, so these are the governing equations, fine, but there is more that we can say about these governing equations. In some specific scenarios, there is something more that we can say, and the way we will say it by considering circulation, which is defined as, okay, which is defined as this C of x is a closed loop of fluid particles. So what I am trying to say is that, reverting back to our discussion on continuum kinematics, let us say in the initial configuration this is a closed loop, this is not a 3D body, this is a closed loop, C, let us call it as C naught of capital X. Okay, as the fluid flows, this loop is going to deform, tumble around and do a lot of things. Okay, and at some time t, so this is at t equal to 0, at some time t, this loop becomes this C of x, where this x is a function of t. Okay, so this x is a function of t. Okay, and what I want to look at is the time rate of change of this circulation. Why am I looking at it? It will become clear in a minute. Why am I looking at it? It will become clear in a minute. So d gamma over dt So this becomes the material derivative because gamma is going to be a function of your, actually it doesn't matter if you specify it as a material derivative here or not. So we are going to apply the same transformation that we did when we derived the Reynolds transport theorem. I cannot take this derivative inside because my integration limits are functions of time as well. So I'm going to write it as some C naught and then u dot. So what was dx, if you recall? It was the, oh, opposite. It was the deformation gradient was defined as this del x by del capital X. So this dx will be simply, okay, and the reason of doing this is because my limits are not functions of time anymore because these are material coordinates. My limits are not functions of time anymore. So I can take this d by dt inside and I will get, so this was the exact same way how we derived the Reynolds transport theorem. So we will get a du by dt dot with f dx capital plus a df by dt and a u dot, so u dot df by dt dot dx. And now let us just look at the second term. So this u dot df by dt dot dx, if I write it in the index notation, it becomes ui df small I capital J by dt dx capital J. And we have calculated this. We have calculated this df small I capital J dt. We have calculated this. What does it become? This was actually equal to, so df by dt was actually equal to f dot with gradient of velocity. If you go back, you will notice this, that we have derived what is this df by dt. So this actually becomes f, actually it becomes grad u dot f, not that one. So this becomes del u I over del x small p f of p capital J. Okay, and then when you substitute it here, this will become, so u dot df over dt dx will become ui del ui over del xp f pj dxj. f pj dxj is nothing but d small xp. So this is ui del ui by del xp d small xp. And now if this integration is done along a closed curve, what is this? Ui del ui by del xp dxp. So if I am doing this integration, so if I am doing this integration along a closed curve, I don't know what this has become black color. So this is nothing but del by del xp of ui by 2 dxp. along a closed curve. What is this integration? What is this integration along a closed curve? It's a complete derivative. So this will be at final minus initial points, which are the same. So this is 0. You are integrating along a closed curve. You have a full complete derivative inside, so it will be just the value at final point minus value at initial point, which are the same points. So the integral is 0. So this second term we have shown that it is actually equal to 0. The first term, if you look at it, the first term, which is du by dt dot with f dx, that is actually equal to, so if you look at du by dt, capital Du by dt, that is from here for inviscid flows. So we are doing this for inviscid flows. So minus 1 by rho I can keep outside, and this becomes grad of p dot f dot dx, which is again minus 1 by rho del p over del x I d small x I over a closed integral, which is again 0. So that means for inviscid flows, the rate of change of this circulation is actually 0. This is 0 for inviscid flows. The meaning of this is that, remember, this circulation is defined by integrating over material curves, okay, closed loop of fluid particles. So this loop is found by joining some random fluid particles, and I am forming a closed loop by them. So let us say there is a flow coming towards a body, okay, there is a flow coming towards a body, and far upstream, so let's say this is your body and there is a flow coming towards the body, and far upstream in the flow there is no vorticity, okay, far upstream in the flow there is no vorticity. From circulation, from Kelvin, from Stokes theorem, you know this is going to be equal to vorticity times integral, vorticity integral inside the area, okay, inside the area defined by this Cx. So if there is no vorticity in this area of curve defined far upstream, then as long as you are in the inviscid flow regime, there will not be any vorticity that will appear in the flow. That is what this theorem, which is called Kelvin's theorem here, specifies, that for inviscid flows the rate of change of circulation gamma is 0. So if initially you don't have any circulation, you will not develop any circulation later on also. So initially, if along any closed loop you have u dot dx 0, or inside this closed loop you have omega dA 0, then as long as you stay far away from the boundaries, let's say this is how this loop looks, there is no vorticity inside this as well. As long as you stay far away from the inner regime where inviscid flow equations are valid, as long as you are in the outer regime, the Kelvin's theorem states that there is no vorticity that develops. Okay, and this we will use to study ideal flows in the next class.